So let's talk a little bit about some of the other essentials here, getting down into a little bit more of the mechanisms of doing product. Oops. So schedules and releases. Um, of course, things get more complicated as you actually get customers. The reason for existence of the company is to have customers that use your products, use your technology. And uh, having customers is a real hassle. It makes things a lot more difficult to manage, but it's better than the other alternatives. Not having customers is a lot worse, which means that you're going to be working both on things that are incremental improvements, typically because as you engage with current customers, you're going to learn things about how your product works and learn things about what they need. It's great if you start with a minimum viable product that customers like, but you're going to learn even more about what customers want and need and like after they have taken a first product. And so there is naturally going to be a process of incremental improvement on that. At the same time, you also will be learning a lot more about what the technology makes possible and what the mega trends in terms of customer demand look like. What are the issues that customers coming up over the horizon are really trying to deal with? And that may mean that you're also working on major upgrades, second generation product over time. And so you're going to have to find ways to potentially do both in parallel, either in the same organization or having two subgroups which are working on this, both doing minor and major things. Now, there is a temptation that what's commonly called the second system syndrome, where the team does a first release, they do learn things from the first release, and they commit themselves to building a second product which is perfect and incredibly advanced on in every dimension. And they build something far more ambitious as their second product than as their first. And because resources are still limited, this second project becomes so much work, is so comprehensive that it takes forever. That you built the first product in 9 months and the second product takes 3 years. Now, sometimes your first product is so successful that you can survive that 2.25 year drought between the first product and the second product. But more often, what you find when you do that is that a lot of that second product doesn't serve its intended purpose, that it's too ambitious and it's too late. And so you have to think a priori about what the best pattern is for minor releases versus major releases so that you don't fall into the second system syndrome. You also have to think about what the nature of your technology and product is to figure out whether it is fundamentally monolithic. That is, it has one big thing at the center of it. Think of an operating system, right? Lots of moving parts internally, but they're so closely connected that you can't really think about modular upgrades to them versus something which in fact may have lots of interfaces to it that allow you to add customer value in a quasi-independent way, such that you're able to add a module for this or a module for that. If I think for example, in Tensilica terms, we would have efforts to say, no, we're going to build a new fundamental pipeline for the machine. And lots of the pieces, the the architecture, the simulator, all of the base instruction set, all of the major modules have to be rethought of in the light of that new pipeline. On the other hand, there were obvious modules that worked in the Tensilica system, like instruction set extensions for uh, in the audio domain, which were largely orthogonal to the base architecture, and where we could make lots of incremental upgrades to the product, at least for a certain class of customers, without touching the rest of the product. Uh, Certainly, if the nature of the customer's problem and the nature of your technology allows you to upgrade on a component basis, um, take full advantage of that, because that allows you to get incremental customers. It allows you to make incremental improvements to the utility of the product for many customers. Uh, but not all innovations are going to take on that form, because monolithic upgrades take time. They require a level of verification. They may be more disruptive to where customers have made investments, but they may be necessary to making fundamental progress. But when you have components, you also have to think about the compatibility matrix. For example, in the Tensilica case, um, we might say that this new audio DSP option works across all of the different pipelines we offer, but it has to be tested. And there may be subtle incompatibilities or subtle performance differences that have to be characterized as you build out that matrix of compatibility. So there are trade-offs at work. Often the nature of the technology itself will dictate whether it's more monolithic or more component oriented, but you also have some choices to make, which are part of strategy for the size of the steps that you take moving forward. Are you making many, many small steps, or many steps in different, somewhat parallel directions serving different customers? Or do you have one big thing that marches forward in giant steps where you may not be releasing new things even as often as once a year, say? I think there are dramatic changes taking place due to AI-based software development, because now an awful lot of low-level coding is driven from these natural language prompts. Then you have much greater opportunity to build important pieces, major pieces of new functionality in relatively short initial development times. And you may also have opportunity to do a significant amount of code review and unit level testing using the AI tools. But the strength of the AI coding tools as they stand today, which tends to be incredible at low level, may mask the fact that AI software development tools are often remarkably clueless about the big picture. They often are pretty clueless about what the high level objectives are, what the high level optimizations are. Certainly in my own experience, they are really quite junior programmers, masterful coders, but often very ill-informed about the larger principles of how large software systems come together. So you have to watch out for that. I think net, it's going to make it much more economical to build many small incremental improvements in software, including much more customization. That once upon a time, you couldn't consider doing custom variants for every customer, because the coding and testing of those minor variants was so onerous that there wasn't a return on investment. Customers couldn't pay for the effort you put in. I think that we're going to see a world in which there's much more customization because the cost of developing a small variant, changing the user interface a little bit, changing the behavior of one subsystem a little bit will become the cost will become so low that um, it will make sense to do a business in minor variations. We'll see over time. We're still early days on the AI-centric software development. I'm curious how that corresponds to what you all see in thinking about this, the impact of AI software development. All right, well, I'm going to move on. I want to finish up here and leave more time with B. Okay, something.
Well, I can say that I was trying to get some answers from Gemini 3 yesterday and today about running some open source code, and it's just terrible.
Yeah.
It's very surprising because I was thinking, okay, it open source, everything is open source. I'm pointing to a specific GitHub directory, and it gives completely nonsensical things.
Yeah. Certainly some of that does happen for sure. There's no doubt.
I recently did a project from scratch by talking with an LLM and using another LLM as a judge and going back and forth. And usually I give very detailed instructions, etc. And I was pretty happy with the result. Like without writing any code myself, it could create a 2000 line project on some very technical thing that normal software engineers wouldn't know about. It's a bit audio AI kind of thing. So I was pretty happy with the result. Although I saw sometimes it struggles with things that that surprises me. For example, since I am combining two LLM, two codes coming from two different LLMs, and one of them defines one parameter as n and the other defines another parameter as n, and then when combined they get confused. These kind of things that I assume that they could understand from the context of the functions, but they couldn't.
Yeah. Yusuf, how do you, let's say, do you make the interaction between the two? I mean, do you do it manually, or is there like, is it like an automatic thing, like a ping pong game? I mean, or...
I'm new into this, so I did it manually. I'm talking with both of them together and getting output from one of them and giving to the other. This is the function written for this purpose, and I give it criteria to use in evaluation and revise and etc. But I'm very detailed in instructions. I give the criteria to use or specific instructions, what to include, the documentation, etc.
Yeah,
and the quality of the code is great. I mean,
yeah, I have also a similar experience. So I'm developing, let's say, a product and I use the bottom-up approach. So I think about the problem, I come up with the steps, and I do what I need to do. And sometimes when I just don't want to spend time on a step, or let's say I don't have enough, let's say, experience with one of the steps of the process, I delegate it to one of those LLM or vibe coding tools. So I share your experience. So I find that they are good when you give them detailed instructions, and when you break down the problem into, let's say, chunks, because I mean you know that the global vision of the thing. On the other hand, if you try a top-down approach, so for example, one of my colleagues does this. So he starts by like a set of high-level, let's say, requirements. Let's say you need to develop a web app and which shows this kind of things, let's say, and they describes the functionality. So after many iterations, you still see that the code is very kind of black box. So you don't know which part of the code does what part of the process, and you end up with code which is not working. So the quality is not as good as when you architect the thing yourself and you just delegate more steps to the vibe coding tool.
I'd like to try and finish up here because I'm really eager to get going on the conversation with Beatrice. Let me just briefly talk about software development tools here. I think there's been such a transformation in the last 10 years, say, as agile development has become such a popular concept or structure or process that it's worth thinking about this. Now, in early days of a startup, you often don't have as much structure as you would in a stable, established organization. But it's usually some mix. There is a kind of traditional software development, which is particularly appropriate if you know there's a lot of work to do, but the work is familiar, that you can successfully take a large task, break it down beforehand into small pieces, map out the dependencies, put it all into a project management context, and then work to that schedule where all of the partitioning of the problem really happens up front, and then you're just measuring progress as those individual components are built and integrated together. On the other hand, you have ad hoc processes where you accept the fact that it's difficult to foresee how the task will need to be partitioned. You work sort of flying by the seat of your pants, but it's very difficult to make schedules because there are all these unforeseen issues. Dependencies are not known and therefore managed rather loosely and late. And the schedule is changing usually constantly. And there may be a program manager who coordinates that, but you're only relying on rather vague statistics like, the average programmer writes and productizes 50 lines of code a day. Well, that varies by orders of magnitude depending on what kind of a problem it is, and it really overlooks the fact that the problem or your understanding of the problem may be changing a great deal. So the risk here, of course, is that, everybody's writing 50 lines of code a day, but which 50 lines changes every week. Agile development is a process that tries to find a middle ground, a sense, between this highly structured and unstructured approach by creating closely coordinating teams who are tasked to work on very finite goals and with a lot of communication to be able to reset goals on very fine grain, even with daily scrums to coordinate and make small corrections, and then sprints, which are medium-term goals, where people know that they're trying to hit intermediate goals quickly, and then the new goals for the new sprint will be created only once the current sprint is completed. And I think many organizations find that that's a good compromise between an overstructured process, which gets out of date because it's naive to think that you could partition the task completely in advance, or the completely ad hoc process, which doesn't mandate the level of communication to understand where things are as much as Scrum does. And I note again that AI software development may change these trade-offs quite a bit because then the Scrum team may be you and the AI tools, and that you're a whole Scrum team by yourself, where you are the facilitator and the product manager, and you're just fitting into some much larger structure, but you may be responsible for a much larger piece of the total code base. I think there are sort of some classic understanding of the pieces of agile development, particularly in the software area. There is a focus on discovery. There's a focus on the fact that customer needs are changing, that this is accomplished through a lot of face-to-face contact and collaboration, that there is an emphasis on building the minimum necessary code or the minimum necessary design to get the immediate job done. And there's a process of reflection to ensure that process improvements are made, not just design improvements. Not everything's going to fit this kind of a model. If you're doing high-risk research where you may work for months with an uncertain outcome, because in fact you are trying to develop perpetual motion, for example, it may not fit this agile model, which sort of assumes that there is continuity in the development, that in 1 week of focused work you can move from point A to point B. Often in some types of more researchy things, you don't know anything about whether you made progress in a given week. It's part of a much larger experiment with a much larger feedback loop. So I think the mechanisms are fairly well documented. If you don't know it, it's worth doing a little bit research on sprints and scrums and Kanban boards, which is kind of a visualization technique that simplifies what the status is of different subtasks. There's some other principles like pair programming or extreme programming that is explicitly collaborative. I think this changes a lot in the context of AI. Test-driven development, you write the test first. It's really like saying, well, let's write the spec first. I think it's part of that same philosophy that I think RJ here mentioned it. In the whole product development concept, write the press release first and then work backward from the press release to what you're going to build into the product. I think continuous integration and continuous delivery are capabilities that again make sense, particularly if the nature of the development is more incremental. Daily stand-ups, having everybody talk to one another both builds the social connection by which you understand what the strengths and weaknesses are of each team member, but also lets people know what's really happening. And these feedback mechanisms are essential. Whether you do anything else in the agile development, having mechanisms by which you do postmortems and reviews of what worked or didn't work over the last week or the last year do a lot to improve the capabilities of the organization over time. I'm not going to talk a lot about software testing. I think a lot of you already are deeply involved in these sorts of things, but I think it's important to recognize that testing has to take place at many levels of abstraction. And the thing which is most different as you build new product is the production level testing, because what you're building is often a new concept of what customers are going to assume. It's a new workflow, not only for you, but more importantly for your customers. And the definition of what does it mean for the product to be right is highly dependent on what that ultimate customer use case is. So that you need to think about that first. And it's the hardest thing to automate. It's the hardest thing to get AI to do for you. And it often is the most exposed to the customer experience. So in many ways, you want to think about that first, and then think about integration testing, and then think about unit testing in order to understand what you need to accomplish. Some of you are building hardware, and that's great. Hardware testing is a high stakes game because the fundamental costs of a bug are many orders of magnitude higher. If there's a software bug, say that makes it into the product or into the prototype, then you may have an hour a day, maybe even a week to go figure that thing out. And it may have customer impact, which is embarrassing, but everybody knows that the recovery is a bit more straightforward. A hardware bug can mean a setback of 18 months, 2 years, 36 months, can be a huge thing. Companies go out of business because of a single hardware bug. Few companies go out of business because of a single software bug, which means that you need to think about simulation environments to pull as much testing as possible forward into that which can be simulated. And therefore, you need to think about simulations at different levels of abstraction, from SPICE circuit simulations up to high-level, system-level functional simulators and the like. I think one thing which makes hardware hard is that hardware is parallel. You innovate in hardware because silicon density gives you incredibly high degrees of theoretical parallelism available to you. You can do a million things at once in the hardware. Now, sometimes that million-way parallelism gets percolated down into the software model such that it's exposed to people who are developing application. But more often, there's some abstraction that allows you to leverage that hardware parallelism without making a single software algorithm as parallel, or at least not as visibly parallel. But hardware parallelism creates the chance of many, many low probability interactions, race conditions at many levels of abstraction. And so it's often very difficult to debug the hardware parallelism because of the number of low probability interactions, low probability bizarre orderings of events that take place. And so a lot of the challenge in testing hardware is trying to figure out what are you going to do to exercise low probability interactions. In that way, it can be quite different from much software interaction, which relies on a principle of the ordering of things, of sequentiality, which is not a luxury that hardware has. And as a result, hardware tends to follow stricter protocols of modularity, stricter interface protocols. There's a role for third-party verifications of interfaces. And you have additional complexities that come from prototyping. Simulators give you lots of visibility. You can look at anything in the design easily enough. You have the equivalent of source level debug. Prototypes are often these black boxes, often these little chips of silicon, and you only get to look at the pins. You can't look at anything inside. And so you may need to both get very good at reasoning about what is invisible and the development of new hardware software mechanisms to gain more observability into what's going on. And that's a very tricky part. And thinking about bring up becomes a really important part of even the fundamentals hardware design and system design. So there are special difficulties in hardware testing. Documentation, yeah, critically important because people can't read your mind, and you can't read other developers' minds to what's going on. In the old days, you'd write a book, then you'd post a book. Today, things are more minimal. I think the emergence of ChatGPT tools in which every piece of documentation really becomes a dialogue are critically important. Recently, Go-Ching and I wrote this book on essentially Cisco's internal AI development methodologies. And we built it realizing that nobody was going to read the book, but they like to have a book on their desk. The most useful manifestation of of the book was a chat interface. So you go and you chat with the book to figure out different aspects of these design methodologies. Support varies a lot. Eventually, you will probably get to a place where you have multi-layer support. You have lots of customers, especially if it's a product which is exposed to a broad population. It's a consumer product or it's a professional product that's used widely. I'm thinking of WebEx, for example, which has millions of customers. You have a layer of people who can answer questions. These are call centers. This is increasingly automated by AI. And part of the purpose of this first layer is to figure out which are the hard questions and which are the easy questions. The easy questions are answered immediately. The hard questions are escalated to product or feature specialists. But even there, it's a process of filtering between the questions that they can answer and the questions, hopefully a very small fraction of all questions, which eventually go back to the developers, who are the ones who only really understand the full depth of what's going on inside the product. There's a ton that we could talk about in tooling. Every class of technology has its tooling, but certainly almost every product has software or things that look a lot like software. Logic design looks a lot like software. You're going to need source control. You're going to need bug tracking. You're going to need build systems. You're going to need communication. And you probably will need organizational infrastructure and procedures at some point, project management, some notion of development of user interface concepts that gets handed off in some form, maybe as Figma, UX prototypes that get handed off to developers. You will have tools that are used to make queries about the state of the product. You may have large amounts of computing. I mean, particularly if you're training models or running lots of models, you will be consuming a lot of compute, and that's a natural and good thing. And you may even have physical labs. Sometimes it's a software lab that has, every possible platform on every possible operating system release, so that you can do regression testing. Sometimes it's a physical lab where you're going to be actually bringing up hardware and you have special equipment there. I think all of this tooling is going to go through significant changes in the face of AI-based engineering flows. And so what are the takeaways here? Building a product is a learning process. It's learning about what customers want and really value. It's learning about what's feasible, and it's learning about the capabilities of your own organization. There are lots of changes taking place in the processes, that agile processes and now AI-centric processes are important. As the product grows, as the team grows, as the number of customers grows, how you communicate the exact behavior of the product, how you test the exact behavior, become even more central to success. And so all the things around testing and documentation grow even faster than the product grows. And so thinking through how you're going to manage this process, what tooling and coordination you need, how you're going to test and document, become essential parts. And finally, I'll reemphasize, I think that roadmaps play multiple roles. They're motivational tools, they're planning tools, they're customer communication tools, and you have to stay grounded in reality and build roadmaps which are ambitious but feasible, and make sure that you don't become overwhelmed by letting too much into the product, letting too much into the roadmap, such that the roadmap and progress on the essentials becomes incredibly slow and painful because of the sheer number of things, often not very critical things, that have been committed to. So there's a balancing act at work on completeness versus simplicity, ambition versus realism.